method for making the magnesium sulfate crystals. We're going to carry on today by starting to look at how we can make salts from carbonates. So we've looked at making salts from metals, we've looked at making salts from metal oxides. Today we're going to look at making salts from metal carbonates. Give you a bit of an update as well. How did the crystals turn out from the other day? Well, if I just show you there, you can see there's some really nice big crystals, good rhombus in shape as well, which is always a good sign. And yeah, got a decent yield as well. So we're going to be looking at, we're going to be doing a similar practical today, but we're going to be using different ingredients. So first thing we're going to look at, right? So what is the equation for an acid plus a carbonate? So an acid plus a carbonate, you get a salt. You still get a salt, all right? Because when any acid reaction, make a salt. But this time, as well as getting water, you get carbon dioxide produced. And carbon dioxide is a gas. So it tells you here that water and carbon dioxide are released because the carbonate ions react with H plus ions, and the H plus ions come from the acid. Remember, any acid is a source of H plus ions. If you want to see exactly what happened there, 2 H plus ions plus a carbonate ion. Well, we're saying that it's going to make water. Well, what's the formula for water? H2O. And then if I take away H2O from this side, what am I actually left with? So if I get rid of those 2 H's and one of those O's, the other product must be CO2. So that's what happens when a carbonate reacts with an acid. And it could be any acid. It could be a strong or weak, so it could be sulfuric acid. It could be vinegar, which is acetic acid, or ethanoic acid, I should say. And it could be any carbonate, any metal carbonate. So think of a metal, all right? So let's go with tungsten, and let's put the word carbonate at the end. Tungsten carbonate will react with an acid, all right, to make salt plus water plus carbon dioxide. Here we have an example of nitric acid plus calcium carbonate, which is CaCO3, and it's making calcium nitrate plus water plus carbon dioxide. Bit of a recap here. How did we know that it's going to be calcium nitrate? Well, the first thing is the calcium part comes from the metal in the metal carbonate, and the nitrate comes from the acid that you use. So remember, we need to know that nitric acid produces nitrates, sulfuric acid produces sulfates, phosphoric acid produces phosphates, and hydrochloric acid produces chlorides. All right, just remember that's the slight exception to the rule. So here's an equation, and then what would we observe? Again, going back to last lesson, what would we observe during that reaction? Without me doing it, what would we observe? Well, look at the actual symbol equations. So again, we're taking a solution, all right? So that's a solid dissolved in water. So here's a solution, yep, a colourless solution. We're adding a solid, yep, and we are making another solution, which again will probably be colourless in this case, so I'll explain why in a moment. Water and a gas. So there's 2 observations that you can say will happen here. One is that a gas is produced. And what evidence is there that a gas is produced? You will get effervescence, you'll get bubbles. But there's always another observation. And the problem why students tend to lose this mark is because they always focus on this side. They always focus on the right of the equation arrow. And they think, yeah, there's a gas produced, so I'd see that. That's something I can see with my eyes. I can see fizzing. But what else would happen? Well, look, compare left to right. Right? There was a solid at the start, but there isn't at the end. So the solid has reacted, right? The solid has reacted with the acid and is no longer there. So the solid is no longer there at the end. So there's 2 observations there. You're going to see a solid, all right, slowly disappear, and you're going to see a gas produced, all right? But we're going to take it a bit further, all right? We're going to have a look at, how, with the metal plus acid last week, we realized that there was a gas produced, it was hydrogen. And how do we test for hydrogen? We use a lit splint. Well, today, it's not hydrogen that's being produced, it's carbon dioxide. So how do we test for carbon dioxide? And we have done this before. We did it in here towards the start of year 9. You use something called lime water. And lime water is just calcium hydroxide solution. And lime water, in the presence of carbon dioxide, goes cloudy. So we're going to have to try and prove this now. So I'm going to try this reaction, and hopefully two things will happen. The solid will disappear, we'll get a gas produced, and then we'll test that gas with lime water. So let's equip myself with some goggles. So I'm going to put some lime water into this test tube. Okay, so I don't have my goggles just yet. Oh, I'm just about to pour. So I'm going to put this into here. So lime water, you can see, is a colourless solution. Probably a bit too much there. That'll do perfectly. Okay, so I'm going to keep, there's my lime water in the test tube, which is over that side. And on this side, I'm going to put some sulfuric acid. So I'm going to put some sulfuric acid. Yeah. And again, I'm going to add a carbonate to it. Okay, so let's imagine I'm adding calcium carbonate to it. Okay, and two things you'll see. One, you'll see effervescence or fizzing, as you might call it, and then you hopefully see the solid disappear as well. But how am I going to get the gas from here into there? Well, you could just use a delivery system where you've got a bung with a tube over to here and bubble it into there. But I'm going to use my knowledge of carbon dioxide to my advantage here, because carbon dioxide is actually heavier than air. It's a gas that you can pour quite easily. So what I'm going to do is I will pipette, using one of these, the gas that's produced from there into there, and do it a few times, and then I'll put a stopper or a bung on there to prove that we're getting carbon dioxide produced, and then I'll shake it to see that it goes cloudy. So I'm going to get my carbonate first. Okay. So you can see calcium carbonate is a white powder. Yeah. Why is it a white powder? Well, what's the metal in it? It's calcium, and calcium is in group 2. It's not a transition metal, and group 2 and group 1 compounds form white compounds. So let's just put some of this in. Yep. You can see there's fizzing. So I'm going to suck that gas up, put it in there. Suck that gas up, put it in there. Suck that gas up, put it in there. So getting as close to the surface as possible, just sucking the gas up, putting it in there, and then I'll put a stopper on it. So now I've got to get the lime water and the gas to mix. So I'm going to shake it. And hey presto, the lime water's gone cloudy. So I've just pipetted the gas. I could have just got a delivery tube and bungs and just add more equipment to it. But again, I used the chemistry to my advantage. I know that carbon dioxide will diffuse from there, but I thought, I'll tell you what, it's going to hang around at the top of the liquid for a while. So I thought that's why I could pipette it. And one thing you'll notice as well is that the solid has disappeared. Okay, just a little bit left reacting. You can see those bubbles. But that white solid has disappeared. The two observations have been proven to be correct. And that's true for any carbonate, right? So any carbonate will react with the acid to produce a solution, carbon dioxide gas, which will turn lime water cloudy if you were to bubble it through it somehow. All right. Now, the only difference would be if we use a transition metal carbonate, so let's use copper carbonate, for example, because we know that transition metals form colored compounds, the resulting solution would not be colorless. So this is calcium sulfate. All right, you can see it's a colorless solution. Had it been copper sulfate, it would have been that blue solution we saw the other day. Had it been iron sulfate, it'd be a green solution because the transition metals form colorful compounds. Okay, so there's quite a lot of new chemistry there, but also it's stuff that's not exactly brand new because you've come across it before. Okay, so when we looked at the atmosphere and acid rain, for example, we knew that acid rain has a pretty nasty effect on fish and plants and other wildlife, but also has an effect on buildings. All right. So if I show you a couple of pictures now, buildings and statues, anything made of calcium carbonate. And calcium carbonate is the main ingredient, if you like, in limestone and marble, of which, you know, we build certain things out of. So if we have a look here are two statues, before and after, if you like. So this is a statue that was built in 1908 out of marble, or sorry, limestone. So it's calcium carbonate. And then this is a picture in 1968. And you can see it has been weathered. It's been weathered quite a lot. So what happened then? Why is it weathering so much? This is George Washington, a statue of George Washington, one of the American presidents, one of the founding fathers. And you can see, it looks quite nice when it was first made, but you can see he's looking quite old now. And that's because there has been quite a lot of acid erosion, because the pH of rainwater is decreased over time. Why is that? Well, there's a couple of reasons. Because there are quite a few different acids in acid rain. Rainwater naturally is still slightly acidic. It's around a pH of 5.6 to 6.0. But then rainwater that's acidic, more acidic, has been more prevalent over the last 150 years since the Industrial Revolution, and our thirst for burning fossil fuels really did intensify. So here's one example of how an acid might form. So nitrogen and oxygen. In this air right now, they are not reacting because they've got a very, very, very high activation energy, which means it's a very slow reaction. But if you were to increase the temperature, let's say in a car engine, because car engines get very, very hot, the nitrogen and oxygen in the air combine to make nitrogen oxides, so either nitrogen monoxide or nitrogen dioxide, and these dissolve in rainwater to make nitric acid. So you're getting, every time you drive a car or get on a piece of transport or get on some public transport which uses petrol or diesel, these reactions will be happening, and nitric acid will be produced, right, when the fumes hit the rain clouds. Another one, sulfur dioxide, massive problem. This is a tree that has been stripped bare due to acid rain. It didn't obviously happen overnight, right? Loads of people seem to think acid rain, if you get it on you, you're going to burn. No, that's not the case. But sustained periods of, slightly acidic rain will cause a massive problem to things like plants, which rely on enzymes, because enzymes, you'll learn from your biology lessons, are very specific. They work best at a certain temperature and a certain pH. So if the pH that it works best at is pH of 8, fantastic. But as soon as you put acid rain onto it, it's going to lower the pH, and now all of a sudden your enzyme won't work as well. So sulfur dioxide, which we get sulfur from crude oil, because crude oil is made from dead plants and animals that are from millions of years ago. Mostly carbon and hydrogen, so hydrocarbons we get from them, but there are some sulfur impurities in crude oil which aren't actually removed during fractional distillation. So whenever you burn something that comes from crude oil, sulfur dioxide is going to be released, and you're going to get sulfuric acid. So there's two acids there which are in rain clouds, which probably shouldn't be, and that they're happening because of our causes. We're burning fossil fuels, which means we're going to be releasing sulfur dioxide when the sulfur reacts with the oxygen, and we're going to be making nitrogen oxides when nitrogen and oxygen from the air combine under the heat of an internal combustion engine. And that's causing so we're getting, every time it rains, we're getting a more acidic solution. And here's just two equations. All right, so these two reactions will be happening to our our George Washington statue and that other statue I looked at. The calcium carbonate that it's made of is reacting with the nitric acid to make calcium nitrate and the sulfuric acid to make calcium sulfate. And the key thing here is, is the state symbols. Look, that's what's happened. We've gone from a nice solid calcium compound, which doesn't dissolve in water. Calcium carbonate is insoluble, and it's turned it into a soluble one. So now when it rains again, these things are just going to wash off, right? Which is why the features on those statues are starting to weather more due to acid rain. I doubt if you got close enough to one of these statues, you'd actually see the carbon dioxide being released as well, right? Because like I say, it'd be a very, very slow, sustained period of time that this degradation would occur. But again, using the equations, use the state symbols to show why are these statues weathering at an accelerated rate? Because you're turning the statues from insoluble calcium compounds into soluble ones, which means they're going to wash away. Okay. So we've looked at different ways of making salts over the last few days. Acid plus alkali or acid plus metal oxide makes a salt plus water. Job's a good one. Acid plus metal makes a salt plus hydrogen. How could we test the hydrogen? Squeaky pot test. Lit splint goes pop. And today, an acid plus a carbonate makes a salt plus carbon dioxide plus water. And how would we test the carbon dioxide? Lime water goes cloudy. All right. So again, just to sort of recap what we did last week as well, right? I'm going to show you this bottom equation. I'm going to try and make solid crystals of magnesium sulfate. So I'm going to need an acid. I'm going to need a carbonate. So if I'm trying to make magnesium sulfate, I'm going to need magnesium carbonate and an acid. Which acid will I need if I'm making a sulfate? I am going to need sulfuric acid, okay? Which is what I'm going to try and do now. So again, it's a good recap of the work that you've done for me this week in terms of making crystals, okay? So, there we go. Beautiful. So let's make some more salts. Okay, so I'm just going to get rid of this. Put that over there. Got my Bunsen burner ready. And get my pot of magnesium carbonate and sulfuric acid. Okay. So, first things first, you can see, similar method to last week, heat the acid and then keep adding the solid, so in this case the magnesium carbonate, until it's in excess. I'm going to do it slightly differently because I've just seen that this reaction produces quite a lot of effervescence. And I imagine if I was to heat the acid first and then put the carbonate in, it would fizz, effervesce even more, which could be quite dangerous. You don't want to have hot, nearly boiling acid spraying everywhere. So what I'm going to do is I'm going to first put my goggles on. And then I'm going to measure out the acid. I'm going to add the carbonate whilst it's at room temperature. So again, I'm going to just get, again, 20 to 40 centimeters cubed. So I'll pour this into a beaker. Okay. And then just checking that came out of there, didn't it? Good. I was thinking which bottle it was. Yeah. So I'm going to keep that on the edge there so you can see it. And now I'm going to keep adding the carbonate until it stops fizzing. So again, I don't want to add loads at a time. If I put a big spoon in or a big spatula full, then it might overflow. So you can see we're getting a nice bit of fizz. Okay, I'll get my stirring rod, give it a quick stir. So imagine if I'd done that and the acid was boiling, all right, or nearly boiling. Chances are it would have overflown, which is quite dangerous. So again, I think it could probably take a bit more. Again, you can keep repeating the process until it stops fizzing. You can also, because effectively you're neutralizing the acid, you could check the reaction completion with universal indicator, pH paper, so litmus paper, to see when it goes from being acidic to neutral. All right, so that could work. So again, stir, stir, stir. And one thing you'll notice, all right, the color of the solution. It's not turning a lovely blue solution like the other day when we had copper sulfate. We're making magnesium sulfate. And magnesium, just like calcium earlier, is in group 2. It's formed a colorless solution. So again, I can't see any solid at the bottom, which means it can probably take a bit more. So again, I've just got to be very careful not to over add it. And then give it a quick stir. Oh, stay there. Stay. You see it's rising up. Okay. And then we're getting there. It's getting less and less fizzy, and there's a bit of solid left behind now. So I think we're about there. I'll warm it up gently anyway to try and get even more to react. but I think we're roughly about there. So again, yeah, that's not fizz much at all. Put a big glug in. And you can see it's staying white now, which means that the solid isn't reacting. It's just sort of suspended in the solution, all right, a bit like milk. So if I leave it a long enough time, it will separate quite nicely. Yeah, so you can see it's no longer colourless, which means I've got quite a bit of excess there. So what I'll do now is I'm just going to heat the acid. Okay, so I'll just put this out of the way with a Bunsen flame. Just to see if any more dissolve. And then if any more does react, so if it starts to go colourless again, it means it can take more. So I'll start to add a bit more to it. All right, so I won't spend too long on this. So you can see it's that lovely white colour because there's some excess magnesium carbonate in it, we hope. Okay. So again, I'm not going to rapidly boil it. I'm just going to get it to bubble and then stop. And then I can start the next process. So here's my, I can start filtering it. So I'm going to filter it and then I'll do the recrystallizing. So whilst that's going on, I'll take my filter paper, again, fold it into halves, quarters, eighths. We'll do it the grown-up way. And then you've got it as a V. And then fold one half of the V back on itself. And then the other half of the V back on itself. And then hopefully, coffee filter. Yeah, no, there's no more actually dissolving or reacting in there. So I know that I've got an excess of the carbonate. I can turn that off. And now I can filter it in there. So to filter it, obviously that's going to be quite hot on top now. So, handling hot liquids, all right, could be use a tongs of some description, or I could use my trusty blue paper towel. So if I fold my blue paper towel up and up again, now, hopefully, rotate it and then pinch it together, it can act as a little handle. So if I pour this through, into there. So you can see I definitely had some excess of magnesium carbonate left over, and that's just proven it nicely. So I know that all of the acid that I had originally has reacted because I've got some of the solid left over. And again, you can see if this filter paper is doing its job properly, it's coming through as a nice colourless solution. Why is it colourless? Well, it's got magnesium in it, which is not a transition metal. Right? Had it been iron, it'd be green. Had it been chromium, it'd be green. Right? So again, the transition metal compounds are coloured by nature. The group 1 and the group 2 metal compounds are not. So whilst that's going on, I need to set up the final part. So again, just like we did the other day with our blue crystals, I'm going to recrystallize this. So I'm going to replace my gauze with a clay triangle. And then, hopefully that's not a crack. Get rid of any dirt. Fine. Now you can see there's my lovely colourful solution. That's got my magnesium sulfate dissolved in it. I'm going to try and get the crystals back through process of crystallization. Okay, so, all right, perfect. Like I say, I'm not worried about how much I get. Perfect. And now, just like I did the other day, I'm going to heat it until the crystallization point. That's the point at which I just start seeing solid crystals formed. So again, I'm going to heat it on a very roaring flame to get it going. All right, and as soon as I start to see it bubble, I'm going to turn it onto a half and half flame, so we get a nice steady boil. Okay, and then because this is magnesium sulfate, I should end up with a white compound or slightly translucent crystals at the end of it. So hopefully I'll be able to show you that for our next lesson. So just keep an eye on that. Yeah. And it's just about to bubble. So I think I saw my first bubble just then. It's not easy with the lights on for this one because it is a colourless solution. So we're dealing with a colourless solution. So seeing them boil is a little bit trickier. Imagine lemonade versus Coca-Cola. Which one's easier to see bubbles in? So go half and half, get a nice steady simmer. All right. Okay, and then I'm just going to basically heat that to crystallization point, leave it, and then I will pat it dry with towels after about 24 hours, 48 hours. So these crystals, for example, well, all the solution has evaporated from these, all right? But, you know, if I'd gone back a couple of days, I would have just patted them dry with a towel. So all that's hopefully in the 6-mark method that you looked at this week. So again, just showing you another way of making salts, exactly the same method. You add the solid in excess, filter the excess, and